Okay, hello. Let's start with homework 8. I don't want to read whole question. I will go one by one and explain my work. What is deterministic queue automation? DQA. DQA is similar to deterministic push-down automation. Expect that instead of stack, okay, we have queue. The queue allows symbols to be added only the left hand end, I mean the push automation, and the queue allows symbols to be removed only from the right hand end. Okay. Additionally, like push down automata, the deterministic queue automation has read-only input tape, where input head moves strictly left to right. Okay. And there is a blank symbol at the end of the input, so the automation can detect the end of the input. Each step, in each step in deterministic queue automation, look at the current state. Okay, first look at the current state, and look at the current input symbol. Okay. Or the blank at the end, I don't know. Third, look at the symbols at the right hand end of the queue, if any. Okay, if any. Then fourth, decide to push a new symbol onto the left end of the queue. Remove the symbol from the right end, or do neither. This was the first step. I don't want to write whole thing, I just want to mention. Okay. The 5th step is move to the new step, and 6th, advance the input head to the right if there is more input. The deterministic queue automation accept if enters an acceptance state with the input and queue in the right condition depending on the definition. Key idea: simulating by a Turing machine. By Turing machine. A Turing machine can simulate any model with limited or structured memory like Q, okay, by systematically representing that memory on its tape, okay, or tapes. That can be more than one tape, okay. The main question is how do we store and manipulate to the Q on the Turing machines. It's representing the Q on Turing machine type. It can be Q is sequence of the symbol where new symbols are added on the left, or symbols are removed from the right, rear. In front, new symbols are added on the left. In the rear, symbols are removed from the right. Okay. Let's show we can store the sequence on a Turing machine tape from left to right. For instance, let's give an example. Okay. Let's make this and Q1, Q2, Q3, Q10, left end push, this is push, right hand pull. Q1 to Q, not Qn, let's call it N. Q1 to Qn represent the symbols currently in the queue. Okay. By the way, I am checking the time because screen recorder doesn't allow to record more than 10 minutes. Okay, so that the keyboard or mouse sounds coming from that. Okay, I'm not copying anything. Then we might place special markers such as hashtag sharp, from the C# to donate the boundaries. Pushing a symbol means inserting it just after the left boundary. Pulling a symbol means removing the rightmost symbol. Okay, rightmost symbol. A Turing machine can insert and delete tape symbols by shifting data left or right. If it's a single tape Turing machine, there are I think four we did in lecture. There are many type of Turing machine, or by writing a blanks over symbol and rearranging as needed. Okay, using multi-tape Turing machine can make the even clear on a tape for one tape for input, another tape to store Q symbols, and possibly another tape for the control logic. Okay, 0 or 1, as you remember from the lesson transitions. But even a single tape Turing machine, we can do it. Okay, because they all have same power. Okay, this same power, all Turing machine type, but it's not equal with the same speed. Okay, because as you remember from the algorithm lesson, we have time complexity, so that it's not the same speed. Okay, what did we say? Tape movement become more elaborate. Okay, simulating one deterministic queue automation. Step on the Turing machine. A single step in the deterministic queue automation depends on current state. Okay. Simulating one deterministic queue automation. Step on the Turing machine. By the way, let's check time. Okay, I will pause video and continue because my screen recorder doesn't allow to record more than 10 minutes. I am doing on the iPad because I want to sketch or show my work in here, so that I will stop my video. Okay, I have recorded first part, then continue with the second part. We were saying simulating one deterministic queue automation step on the Turing machine. A single step in the deterministic queue automation depends on the current state of the deterministic queue automation and the current input symbol or blank. Thirdly, the rightmost symbol of the queue or nothing if the queue is empty. Okay. From this, deterministic queue may push add symbol to the queue left hand, pull, okay, remove the rightmost symbol, move to the input head one step to the right unless input is finished, transition to a new state. On the Turing machine, we store deterministic queue automation current state somewhere in the Turing machine's tape, or finite control if we represent states as part of the Turing machine control. We read the current input symbol, okay, current input symbol. We locate and write rightmost Q symbol by scanning where the Q symbol are stored. According to the deterministic queue automation transition functions, We perform a corresponding push or pull operation on the tape. We move the input head right by one cell if needed. We update the stored current state to the new state. Thus, each single deterministic Q automation transition can be broken down into finite number of Turing machine moves. I mean, scanning, writing, erasing, or shifting. Okay. Then let's add one page. Detailed simulation step. Let's detailed initialization. Determine the next transition. Perform the Q operation. Okay. Move to the input head. Update the state. Accept or reject. Okay. First, initializations. Initialization. The Turing machine starts with the blank Q region, just a border marker, sharp, okay, from C sharp. I love C sharp, by the way, to represent an empty Q, okay. The Turing machine writes the deterministic Q start state, say Q0 maybe, in some designated location on the tape, or remembers it's in the control, okay. The Turing machine's input head at the leftmost symbol of the input. Then determine the next deterministic Q transition. The Turing machine reads current state. Okay, it's read current state. Then the current input symbol. Okay, or blank. They're needed. Thirdly, the symbol at the right end of the Q, if any. Okay. I don't want to write all thing. From this, it's look up the appropriate deterministic Q transition, what symbol to push, if any, whether to pull the new state, and whether to move the input head. Okay. And third, perform the Q operation. If pull is required, the Turing machine erases the rightmost Q symbol from its tape. This can be done by moving to the symbol and writing a black, then shifting tape content if needed. If push is required, the Turing machine insert a new symbol push just to right and the left boundary, and the sharp symbol, okay, sharp symbol, the boundary. The Turing machine can shift the Q content one cell to the right if necessary and write the new symbol its located cell, okay. Then 4, move the input head. If the deterministic Q transition calls for advancing the input head, the Turing machine, let's call TM, moves its input tape head one cell to the right. Okay, in single tape scenario, I mean, it means carefully returning of the input region and moving that head to the right. Okay, then 5. Update the state. Sorry. I forgot English. Okay. Update. state. It's kind of exciting to speaking and writing, telling something. So I appreciate the teachers. It's really hard. Okay. The TM overwrites the old state or updates its control to record a new deterministic queue automation state. Then accept or reject. If deterministic queue automation enters the acceptance state, and possibly after finishing the input if they're required, the TM transitions to its own accept halting state. Okay. If deterministic queue automation would reject to the TM, it can transition to reject or halting state. If no valid transition applied, the Turing machine rejects by halting in a reject state. Okay. Let's conclusion. A Turing machine can store the queue content on its tape or tapes. Okay, that can be more than one tape. Each push operation can be simulated by inserting symbol on the left and the front of the tape region. Each pull operation can simulate by removing symbol on the right of the region. The Turing machine can track deterministic queue automation current state and inputted position in exactly the same way. Okay. Therefore, every step of deterministic queue automation can be simulated by finite sequence of moves on a Turing machine. This shows that any deterministic queue automation can indeed be simulated by the Turing machine. Okay. This completes the proof. Thank you for watching, and sorry for late submission.